Light speed versus warp speed. It's the ultimate cosmic showdown that has captivated humanity since we first dreamed of traveling to the stars. On one side, we have light speed, the universal constant, the cosmic speed limit that nothing in our universe can exceed. On the other, we have warp speed, the theoretical possibility of bending space-time itself to achieve faster-than-light travel. Today we're diving deep into the physics, the possibilities, and the mind-bending implications of both. If you're fascinated by the fundamental mysteries of our cosmos and want to explore the deepest questions in physics, make sure to subscribe to this channel and give this video a thumbs up. Now let's begin. To understand this cosmic competition, we first need to grasp what each contender truly represents. Light speed isn't just about how fast light travels, it's about the fundamental structure of space-time itself. When Einstein revealed that nothing can exceed the speed of light, he wasn't imposing an arbitrary rule. He was describing a fundamental feature of how space and time are woven together. Light travels at exactly 299,792.458 kilometers per second in a vacuum. This isn't just the speed of photons, it's the speed of causality itself, the maximum rate at which cause and effect can propagate through the universe. It's the speed of gravitational waves, the speed at which electromagnetic fields update, and the speed that defines the relationship between space and time. But here's what makes light speed truly special. It's the same for everyone, everywhere, regardless of how fast you're moving. If you're racing toward a beam of light at half the speed of light, that beam still approaches you at exactly light speed. If you're running away from it at 99% of light speed, it still catches up to you at exactly light speed. This constancy isn't a quirk, it's what makes the laws of physics work the same throughout the universe. Now let's talk about what happens as you approach light speed. According to special relativity, three dramatic effects occur. First, time dilation. Your clock slows down relative to stationary observers. At 90% of light speed, time passes about half as fast for you. At 99.9%, time slows by a factor of 22. At 99.999%, a year of your time equals 70 years for someone at rest. Second, length contraction. Distances shrink in your direction of motion. That journey to Alpha Centauri, 4.3 light years away. At 99.9% of light speed, it appears to be only about 60 light days away from your perspective. The entire universe compresses in front of you like an accordion. Third, mass increases, or more accurately, the energy required to accelerate you increases without limit. As you approach light speed, it takes more and more energy to gain each additional meter per second of velocity. To actually reach light speed, you'd need infinite energy, which is impossible. The universe has built-in protection against breaking its speed limit, but warp speed operates on completely different principles. Instead of moving through space, warp drive moves space itself. The concept, first rigorously described by physicist Miguel Alcubierre in 1994, involves contracting space in front of a spacecraft and expanding it behind. The ship sits in a bubble of flat space-time, never exceeding light speed locally, while the bubble itself moves through space faster than light. Think of it like this. Imagine you're on a moving walkway at an airport. Even if you're standing still on the walkway, you're moving relative to the terminal. Now imagine the walkway can move faster than you could ever run. That's essentially what warp drive does. It moves the cosmic walkway, space-time, while you remain stationary within your bubble. The mathematics of warp drive comes straight from Einstein's general relativity. There's nothing in the equations that forbids space-time from expanding or contracting faster than light. In fact, we know this happens. During cosmic inflation, space expanded much faster than light. Even today, galaxies sufficiently far apart are receding from each other faster than light due to cosmic expansion. The space between them is growing faster than light could traverse it. Recent research has refined Alcubierre's original concept. In 2021, physicist Eric Lentz proposed a new class of warp drive solutions that don't require negative energy, a major theoretical breakthrough. His soliton solutions use positive energy configured in specific patterns to achieve the same space-time warping effect. While the energy requirements remain astronomical, this development moved warp drive from probably impossible to incredibly difficult, but maybe not impossible. The Breakthrough Propulsion Physics program, run by NASA from 1996 to 2002, seriously investigated warp drive possibilities. While they didn't build a working drive, they established important theoretical constraints and identified key challenges. The program's legacy continues in various research groups worldwide, including Harold White's work at the Limitless Space Institute. The energy requirements for warp drive reveal the staggering challenge we face. Alcubierre's original calculation suggested that moving a small spacecraft faster than light would require energy equivalent to the mass energy of Jupiter, or even the entire observable universe, depending on the configuration. That's using Einstein's E equals mc squared to convert the entire mass of Jupiter into pure energy. Even with Lentz's improvements and other optimizations, we're still talking about energy equivalent to hundreds of solar masses. But let's examine what recent experiments have actually achieved. In 2013, Harold White's team at NASA's Johnson Space Center conducted experiments with a modified Michelson-Morley interferometer, attempting to detect microscopic space warping. While they reported some anomalous readings, the scientific community remained skeptical, as the effects were at the edge of measurement sensitivity and haven't been independently replicated. This highlights a crucial point: we haven't created even the tiniest warp bubble in any laboratory. Meanwhile, light-speed travel, or rather near-light-speed travel, is something we achieve routinely, just not with spacecraft. At the Large Hadron Collider, protons race around a 27-kilometer ring at 99.99999% of light speed. We've accelerated particles to speeds where they experience time dilation factors of thousands. From the particles' perspective, the 27-kilometer ring contracts to just a few meters. The Parker Solar Probe, launched in 2018, holds the record for the fastest human-made object, reaching speeds of about 195 kilometers per second, roughly 0.065% of light speed. While this seems slow compared to light, it represents tremendous progress. The probe experiences measurable relativistic effects, with its onboard clocks running slightly slower than Earth clocks. Let's dive into what traveling at each speed would actually feel like. At light speed, or rather at 99.99% of light speed, since reaching true light speed is impossible for anything with mass, the universe would look profoundly alien. Due to relativistic aberration, stars ahead of you would appear to crowd together, their light blue shifted to higher frequencies. Behind you, stars would redshift and spread apart. At sufficient speeds, the cosmic microwave background radiation would blue shift into visible light, creating a brilliant glow ahead of you. The journey to Proxima Centauri, our nearest star at 4.24 light-years away, would take just over 4 years from Earth's perspective. But from your perspective aboard the ship, time dilation would compress this to perhaps just a few months. You'd arrive at Proxima Centauri having aged only months, while Earth aged years. This temporal disconnect represents one of the profound challenges of near-light-speed travel. You can never truly go home to the same time you left. With warp drive, the experience would be entirely different. Since you're not moving through space but rather with space, you'd experience no time dilation, no length contraction, no relativistic effects at all. You'd be in a bubble of normal space-time, potentially watching stars zip by faster than light. The journey to Proxima Centauri might take days, hours, or even minutes, depending on your warp factor, and you'd arrive having aged exactly as much as observers on Earth. But here's where warp drive faces a potentially insurmountable challenge: the horizon problem. As your warp bubble accelerates, a horizon forms behind you, a boundary beyond which you cannot send signals back to your starting point. Similarly, a horizon forms ahead of you, limiting what you can see of your destination. You'd be flying blind, unable to navigate or communicate with either your origin or destination during transit. Recent theoretical work has identified another major issue: the destabilization problem. Quantum effects at the boundaries of a warp bubble could cause it to rapidly decay, potentially within microseconds. Stefano Finazzi and colleagues showed in 2010 that quantum fluctuations would be amplified at the bubble walls, likely destroying any warp field before it could be used for travel. While some researchers dispute these findings, the quantum stability of warp bubbles remains a serious concern. The causality paradox presents perhaps the most fundamental challenge to faster-than-light travel. If you can travel faster than light, you can, in principle, travel backward in time. This isn't science fiction, it's a direct consequence of special relativity. Faster-than-light travel in one reference frame appears as time travel in another frame. This could create grandfather paradoxes and other causality violations that seem to be forbidden by the structure of physics itself. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics somehow prevent the formation of closed, time-like curves, paths through space-time that loop back to their own past. Every proposed mechanism for faster-than-light travel, including warp drive, potentially creates such curves. The universe might have built-in safeguards that make warp drive impossible, not just difficult. Let's examine the latest research on both fronts. For light-speed travel, the Breakthrough Starshot project, announced in 2016, aims to send tiny probes to Proxima Centauri at 20% of light speed using powerful laser propulsion. These star chips, weighing just grams, would be accelerated by a 100-gigawatt laser array. While 20% of light speed is far from light speed itself, it would still get probes to our nearest star in about 20 years, a human lifetime rather than millennia. The physics behind Breakthrough Starshot reveals both the promise and limitations of approaching light speed with real technology. The project faces enormous engineering challenges, keeping the laser focused on a sail just meters across over distances of millions of kilometers, protecting the electronics from cosmic radiation at 20% of light speed, and ensuring the probe can transmit data back to Earth across 4 light-years. Yet these challenges are engineering problems, not violations of physical law, a crucial distinction when comparing light speed to warp speed. Recent developments in antimatter research offer another path toward relativistic speeds. The Alpha collaboration at CERN has successfully trapped antihydrogen atoms for over 16 minutes, allowing detailed study of antimatter properties. While we're nowhere near having antimatter engines, the energy density of matter-antimatter annihilation, converting 100% of mass to energy, makes it the most efficient possible rocket fuel. A spacecraft using antimatter propulsion could theoretically reach 90% of light speed or higher. But even antimatter rockets face the tyranny of the rocket equation. To accelerate to near light speed and then decelerate at your destination requires exponentially more fuel as your target speed increases. For a journey to Proxima Centauri at 90% of light speed with acceleration and deceleration, you'd need antimatter fuel with mass comparable to your spacecraft, and we currently produce only nanograms of antimatter per year at enormous cost. Speaking of fundamental limits, if you're curious about why the universe imposes a cosmic speed limit in the first place, check out my video Entropy and Light Speed. Why the universe has a speed limit, where we explore the deep connection between thermodynamics, information theory, and the structure of spacetime. Check it out after this video, the link is in the description and on the card above. It'll give you an even deeper understanding of why light speed is so special. Now let's examine what recent observations tell us about faster-than-light phenomena in nature. Quantum entanglement often gets misrepresented as faster-than-light communication, but it's more subtle than that. When entangled particles correlate instantaneously across any distance, no information actually travels faster than light. You can't use entanglement to send messages because the correlations only appear when you compare measurements after the fact, and that comparison requires classical communication limited by light speed. However, there are legitimate faster-than-light phenomena in physics. Phase velocities and group velocities of waves can exceed light speed without violating relativity because they don't carry information. The spot of a laser swept across the moon's surface can move faster than light, but this spot isn't a physical object. It's just where photons happen to be arriving. These examples show that faster than light requires careful definition. Tachyons, hypothetical particles that always travel faster than light, represent another approach to the question. If tachyons exist, they would experience time backward from our perspective and require infinite energy to slow down to light speed. Despite decades of searches, no evidence for tachyons has been found. Most physicists believe they're mathematical curiosities rather than physical realities, but their theoretical properties illuminate the strange consequences of faster-than-light travel. The Casimir effect demonstrates that empty space, the quantum vacuum, has measurable properties that might be exploited for exotic propulsion. Between closely spaced conducting plates, certain quantum fluctuations are suppressed, creating negative pressure. Some researchers have speculated about using Casimir effects to create the negative energy required for Alcubierre drives. However, the effect is tiny and may not provide the type of negative energy needed for spacetime manipulation. Recent astronomical observations have placed constraints on both light speed travel and potential warp signatures. The Fermi paradox, if the galaxy is billions of years old and interstellar travel is possible, where is everybody, becomes even more puzzling if faster-than-light travel is possible. Either we're among the first intelligent species, unlikely given cosmic timescales, or there are fundamental barriers to interstellar expansion we haven't recognized. CT researchers have begun looking for techno-signatures that might indicate advanced propulsion systems. A spacecraft accelerating to near-light speed would produce distinctive radiation patterns. A functioning warp drive might create detectable gravitational waves or other spacetime distortions. So far, no such signatures have been found, but our detection capabilities are still limited. The thermodynamics of space travel presents challenges for both approaches. At near-light speed, the cosmic microwave background radiation blue shifts into intense gamma rays in your direction of travel. The faster you go, the more severe this radiation becomes. At 99.99% of light speed, the radiation would be lethal without massive shielding. This creates a practical speed limit well below light speed for any spacecraft carrying living beings or sensitive equipment. For warp drives, the thermodynamics are even stranger. The bubble of warped space-time would trap photons and particles, potentially creating a caustic boundary of extreme radiation. When the bubble finally dissipates at your destination, this trapped radiation would be released in a burst that could destroy anything in front of you. Some calculations suggest this burst would be powerful enough to sterilize planets, hardly ideal for peaceful exploration. The philosophical implications of light speed versus warp speed extend far beyond mere transportation. Light speed travel, with its time dilation effects, would fundamentally alter human society. Imagine interstellar merchants who age months while their home planets age decades, or explorers who return to find centuries have passed. This temporal asymmetry would create distinct classes of humans: the travelers who skip through time, and the planet-bound who experience every moment. Relationships, economics, and governance would need complete reimagining. Recent studies on long-duration spaceflight psychology reveal challenges that would be magnified at relativistic speeds. The Mars 500 experiment simulating a mission to Mars showed significant psychological stress, even with the knowledge that home was just outside the door. Now imagine knowing that everyone you've ever known will be dead before you reach your destination. The psychological toll of relativistic time dilation might be the greatest barrier to near-light speed travel. Warp drive, if possible, would create different but equally profound societal changes. Without time dilation, interstellar civilization becomes feasible. Trade routes could connect star systems. Families could remain synchronized across light years. But this connectivity brings its own challenges. How do you govern a civilization spread across multiple star systems when each world might develop its own culture and interests? Let's examine the cutting-edge physics that might make one or both technologies possible. In 2022, researchers at the University of Göttingen proposed a new type of warp drive that requires no exotic matter at all. Instead of negative energy, their solution uses a sophisticated arrangement of positive energy densities to create the necessary space-time curvature. While still requiring enormous energies, this approach eliminates one of the fundamental theoretical obstacles to warp drive. Meanwhile, advances in laser propulsion are making near-light speed travel more feasible. The Starshot project has identified key technologies needed: ultralight materials for solar sails, miniaturized electronics that can survive decades in space, and laser arrays that can maintain coherence over interstellar distances. Each challenge is daunting, but none violate known physics. Companies like Breakthrough Initiatives are investing hundreds of millions of dollars in solving these engineering problems. The discovery of gravitational waves by LIGO has opened new possibilities for both detecting and potentially creating space-time distortions. Every gravitational wave detection confirms that space-time is a dynamic, manipulable medium. While we're far from creating artificial gravitational waves strong enough for propulsion, understanding how space-time responds to energy and momentum is crucial for any future warp drive technology. Quantum gravity, the still elusive theory unifying quantum mechanics and general relativity, might hold the key to understanding ultimate speed limits. Some approaches, like loop quantum gravity, suggest space-time itself is quantized at the Planck scale. This granularity might impose fundamental limits on how space-time can be warped, potentially ruling out certain warp drive configurations while allowing others. String theory offers another perspective. In models with extra dimensions, what we perceive as faster-than-light travel might be shortcuts through higher dimensions. Imagine our three-dimensional space as a curved surface in a higher dimensional space. What appears as faster-than-light travel in 3 dimensions might be ordinary motion through a higher dimensional bulk. While highly speculative, this framework provides mathematical consistency for apparent faster-than-light phenomena. Recent observations of high-energy cosmic rays have placed constraints on possible violations of Lorentz invariance, the symmetry underlying special relativity. These cosmic rays, with energies millions of times greater than we can produce in accelerators, travel billions of light-years without showing any deviation from light speed limits. This suggests that even at extreme energies, the cosmic speed limit holds firm. The Parker Solar Probe's successive speed records demonstrate our progress toward relativistic velocities. With each gravity assist from Venus, the probe gains speed, eventually reaching over 700,000 kilometers per hour, about 0.06% of light speed. While modest by cosmic standards, this represents real engineering pushing against relativistic barriers. Future missions using similar techniques but with more powerful propulsion could achieve significantly higher fractions of light speed. Metamaterials research has opened unexpected avenues for spacetime manipulation. These artificially structured materials can bend electromagnetic waves in ways impossible with natural materials. Some researchers speculate that similar principles might apply to gravitational fields. If we can create materials that interact with gravity in novel ways, it might enable new approaches to both near-light speed travel and space-time warping. The economics of interstellar travel heavily favors whoever achieves their goal first. If near-light speed travel becomes practical, the time dilation effect means early interstellar colonists would have a massive advantage. They could establish colonies across multiple star systems, while Earthbound civilizations age at normal rates. Conversely, if warp drive is developed first, its users could establish instantaneous communication and travel networks, making slower-than-light expansion obsolete. The search for natural warp signatures in the cosmos has become a serious scientific endeavor. Astronomers are looking for anomalies that might indicate advanced civilizations using warp drives. These could include unusual gravitational lensing patterns, specific types of gravitational waves, or distortions in the cosmic microwave background. The fact that we haven't detected such signatures doesn't necessarily mean warp drives are impossible. It might mean they're rare, or that we don't yet know what to look for. Recent calculations by physicists like Kip Thorne have shown that traversable wormholes, another form of faster-than-light travel, require similar exotic conditions to warp drives. Both need negative energy densities or exotic matter to maintain their structure. Interestingly, microscopic wormholes might naturally exist as quantum foam at the Planck scale. The challenge is expanding these to macroscopic sizes and stabilizing them for travel. The Unruh effect adds another layer of complexity to near-light speed travel. Accelerating observers experience a thermal bath of particles with temperature proportional to acceleration. At the extreme accelerations needed to reach near-light speed quickly, this Unruh radiation would be intense. Your spacecraft would essentially be flying through a self-generated particle storm, adding to the engineering challenges of relativistic travel. Let's examine what current missions are teaching us about the practicalities of high-speed space travel. The Voyager probes, launched in 1977, are traveling at about 17 kilometers per second, fast by human standards, but only 0.005% of light speed. Even at this modest velocity, they've encountered unexpected challenges like the heliosphere boundary and interstellar medium that future relativistic spacecraft would face at much higher intensities. The phenomenon of relativistic beaming would dramatically affect navigation at near-light speeds. Light from stars ahead would be concentrated into an increasingly narrow cone as you accelerate. At 99.9% of light speed, nearly all the light from the entire celestial sphere would appear to come from a small spot directly ahead. Navigation would require sophisticated computer systems to interpret this distorted view and maintain course. For warp drives, recent theoretical work has identified the stopping problem. How do you decelerate a warp bubble when you're causally disconnected from the space-time outside? Some solutions involve pre-programming the bubble to dissipate after a certain proper time, but this eliminates the ability to adjust your journey mid-flight. Others propose using staged bubbles, creating a series of smaller jumps rather than one continuous faster-than-light journey. The materials science requirements for both technologies are staggering. Near-light-speed travel requires materials that can withstand bombardment by interstellar particles, effectively transformed into deadly radiation by your velocity. Every hydrogen atom becomes a cosmic ray. Warp drives would need materials that can maintain structural integrity at the boundary between normal and warped spacetime, where tidal forces could be extreme. Recent developments in fusion propulsion offer a stepping stone toward relativistic speeds. Projects like Princeton's direct fusion drive could achieve exhaust velocities of 3 to 5% of light speed. While the spacecraft itself would travel slower, fusion rockets could reach a few percent of light speed, fast enough for interstellar precursor missions to the outer solar system and potentially the nearest stars within human lifetimes. The discovery of interstellar objects like Oumuamua and Borisov passing through our solar system has implications for both technologies. These objects prove that material naturally travels between star systems, albeit at modest speeds. If we could catch and analyze such objects, we might learn about conditions in other star systems without traveling there ourselves. Alternatively, these objects could serve as test platforms for propulsion technologies. Quantum coherence presents challenges for both approaches. At near-light speeds, maintaining quantum coherence in shipboard quantum computers would be extremely difficult due to time dilation and relativistic effects. For warp drives, the question is whether quantum coherence could even exist across the boundary between warped and normal spacetime. These issues might limit the computational capabilities of interstellar spacecraft. The biosignature preservation problem affects both technologies differently. At near-light speed, time dilation means that biosignatures from your destination, signs of life in planetary atmospheres, could change significantly between observation and arrival. What looks like a living world when you depart might be dead when you arrive decades later. Warp drive would allow real-time observation, but the energy release upon arrival might destroy the very biosignatures you came to study. Recent models of galactic colonization show surprising results. Even at just 1% of light speed, a determined civilization could colonize the entire galaxy in a few million years, a cosmic eye blink. The fact that we see no evidence of such colonization might indicate that interstellar travel is harder than we think, that civilizations choose not to expand, or that we're among the first intelligent species in our galaxy. The frame-dragging effect predicted by general relativity and confirmed by the Gravity Probe B mission shows that massive rotating objects drag space-time around them. Some theoretical warp drive designs incorporate rotation to reduce energy requirements. By spinning the spacecraft or the warp field itself, it might be possible to achieve the necessary space-time distortion with less exotic matter. The comparative analysis of power generation for both technologies reveals fundamental limits we're only beginning to understand. For light-speed travel, even with perfect mass-to-energy conversion through antimatter annihilation, you face the relativistic rocket equation. To reach 99% of light speed and decelerate at your destination requires fuel mass many times your payload mass. But for warp drives, the power requirements are even more staggering. You need to generate energy densities comparable to those found in the Big Bang itself. Recent experiments with high-intensity lasers have created conditions where virtual particles become real, a phenomenon called pair production from the quantum vacuum. The SLAC National Accelerator Laboratory has achieved electric fields strong enough to start probing the structure of the vacuum itself. While we're nowhere near creating space-time distortions, these experiments show we can manipulate the quantum vacuum in ways that seemed impossible just decades ago. The navigation problem becomes increasingly severe as we approach either technology's limits. At near-light speed, cosmic ray impacts would create secondary particle showers that could scramble navigation computers. the spacecraft would need self-repairing systems capable of functioning in extreme radiation environments. For warp drives, the navigation challenge is even worse. You're essentially flying blind, unable to see or communicate with the outside universe while in your bubble. Let's examine what nature itself might be telling us about these possibilities. Pulsars, rapidly rotating neutron stars, create some of the most extreme spacetime conditions outside black holes. The millisecond pulsar PSR J1748-24468 rotates 716 times per second, with its equator moving at about 24% of light speed. The fact that these objects remain stable at such velocities provides real-world data about matter behavior at relativistic speeds. The cosmic speed limit creates fascinating paradoxes that illuminate the difference between our technologies. The ladder paradox, where a ladder moving at near light speed appears length contracted to fit inside a smaller garage, shows how observers in different reference frames see events differently. With warp drive, no such paradoxes exist because you're not moving through space, you're moving space itself. Recent observations of fast radio bursts, FRBs, have provided new tests of relativistic physics across cosmic distances. These millisecond pulses travel billions of light years, yet their different frequency components arrive simultaneously to within measurement precision. This confirms that the speed of light doesn't vary with energy across cosmic scales. Bad news for theories hoping to find loopholes in the cosmic speed limit. The thermodynamic arrow of time presents different challenges for each technology. At near light speed, you're essentially traveling into the future. Everyone you knew ages and dies while you remain young. With warp drive, you maintain temporal synchronization but risk causality paradoxes. Some physicists argue that thermodynamics itself might prevent faster-than-light travel, as it would allow entropy to decrease in certain reference frames. Breakthrough propulsion. Physics, though no longer formally funded by NASA, continues through independent researchers. Recent proposals include the Mach effect thruster, which claims to use relativistic mass fluctuations for propellantless propulsion, and various approaches to manipulating inertia itself. While mainstream physics remains skeptical, these efforts highlight humanity's determination to overcome the cosmic speed limit. The discovery of time crystals, structures that repeat in time rather than space, has opened new thinking about space-time manipulation. These quantum systems exhibit periodic behavior without energy input, seeming to violate thermodynamics, though they actually don't. Some researchers speculate that similar principles might enable new forms of space-time engineering, though connecting quantum-scale phenomena to spacecraft propulsion remains highly speculative. Consider the biological implications of each technology. At near-light speed, cosmic radiation would damage DNA, requiring either extensive shielding, medical countermeasures, or genetic modification of astronauts. Suspended animation might be necessary for long journeys. With warp drive, biological challenges are different but no less severe. The transition into and out of warped spacetime might subject organisms to extreme tidal forces or unknown quantum effects. The discovery of exoplanets in nearby star systems has made the question of interstellar travel more pressing. Proxima Centauri b, a potentially habitable world just 4.2 light-years away, represents a tantalizing target. At 10% of light speed, potentially achievable with fusion rockets, we could send probes there in about 40 years. With warp drive, we could visit tomorrow. The existence of nearby potentially habitable worlds makes the limitations of our current technology particularly frustrating. Recent studies of plasma dynamics in extreme magnetic fields, such as those around magnetars, provide insights into matter behavior under conditions relevant to both technologies. Plasma confined by intense magnetic fields can achieve relativistic temperatures where particles naturally approach light speed. Understanding these natural particle accelerators helps us design artificial ones that might propel spacecraft to similar velocities. The quantum Zeno effect, where frequent observation prevents a quantum system from evolving, might have implications for warp drives. If spacetime at the quantum level resists certain types of manipulation, it could make creating stable warp bubbles impossible. Alternatively, the effect might be harnessed to stabilize otherwise unstable warp configurations. The intersection of quantum mechanics and general relativity remains largely unexplored territory. The role of artificial intelligence in achieving either technology cannot be overstated. At near light speeds, time dilation means that Earth-based mission control becomes impossible. A spacecraft traveling at 99.9% of light speed experiences such extreme time dilation that minutes on board equal years on Earth. AI systems would need to handle all navigation, repairs, and decision-making autonomously for potentially centuries of Earth time. For warp drives, AI might be essential for managing the complex field equations required to maintain a stable bubble while navigating through unseen space. Recent advances in photonic propulsion offer another path toward relativistic speeds. Professor Philip Lubin's directed energy propulsion for interstellar exploration, DEEPIN, proposes using massive laser arrays to push lightweight spacecraft to significant fractions of light speed. Unlike chemical or even fusion rockets, photonic propulsion doesn't require carrying fuel, avoiding the tyranny of the rocket equation. The spacecraft could be accelerated continuously by lasers based in our solar system, potentially reaching 10 to 20% of light speed. The discovery of gravitational lensing by galaxy clusters has revealed natural phenomena that bend spacetime on massive scales. The galaxy cluster Abell 1689 bends light from background galaxies so strongly that multiple images appear. While this isn't faster than light travel, it demonstrates that spacetime can be dramatically warped by mass energy. Understanding natural spacetime distortions helps us evaluate whether artificial ones for warp drives are feasible. Let's examine the information paradox that arises with both technologies. At near light speed, information from your destination continues arriving blue-shifted and time-compressed. A year of events at your destination might appear to happen in days from your perspective. With warp drive, you might arrive at your destination before light, carrying information about recent events there. Both scenarios create situations where cause and effect become scrambled from certain perspectives. The vacuum catastrophe, the enormous discrepancy between predicted and observed vacuum energy, has implications for both technologies. Quantum field theory predicts vacuum energy densities that would make the universe curve so strongly that it couldn't exist as we know it. The fact that it does exist suggests we're missing something fundamental about spacetime. This missing piece might be the key to understanding whether exotic propulsion is possible. Recent observations of binary pulsars have provided natural laboratories for testing relativistic effects. The Hulse-Taylor binary pulsar system loses energy exactly as predicted by general relativity through gravitational wave emission. These systems demonstrate that massive objects moving at significant fractions of light speed behave precisely as Einstein predicted, lending credence to relativistic calculations for spacecraft propulsion. The frameshift drive concept, proposed by various researchers, represents a hybrid approach. Instead of trying to exceed light speed or warp spacetime dramatically, you make many small spacetime distortions, each below the threshold that requires exotic matter. By rapidly shifting between reference frames, you might achieve an effective velocity greater than conventional propulsion allows, though still below light speed. This approach sidesteps some theoretical objections to both pure light speed travel and warp drives. Quantum entanglement, while not enabling faster-than-light communication, might still play a role in interstellar travel. Entangled particles could serve as perfect clocks, maintaining synchronization between Earth and a relativistic spacecraft despite time dilation. They could also enable certain types of quantum sensing that remain correlated regardless of distance, potentially useful for navigation or scientific observations. The discovery of dark energy has fundamentally changed our understanding of space-time dynamics. If dark energy represents a property of space itself, the cosmological constant, then space has inherent energy that might be harvested or manipulated. Some speculative proposals suggest that warp drives might tap into dark energy, using the universe's own expansion tendency to create propulsion. While highly speculative, this illustrates how cosmological discoveries might enable future technologies. Recent studies of neutrino oscillations have confirmed that these ghostly particles have mass and therefore cannot reach light speed, despite traveling at 99.999% of it. The fact that neutrinos with almost negligible mass still respect the cosmic speed limit reinforces how fundamental this barrier is. Even particles that barely interact with matter cannot break this rule. The concept of chronology protection, proposed by Stephen Hawking, suggests that physical laws conspire to prevent time travel paradoxes. Every proposed method for faster-than-light travel potentially enables time travel in certain reference frames. Hawking argued that quantum effects would destroy any would-be time machine before it could operate. If true, this might be why we've never seen evidence of time travelers or faster-than-light travelers. Observations of ultra-high-energy cosmic rays have revealed particles with energies that challenge our understanding. The Oh My God particle, detected in 1991, had energy equivalent to a baseball thrown at 60 miles per hour, compressed into a single proton. Understanding how nature accelerates particles to such extremes might reveal principles applicable to spacecraft propulsion. The holographic principle suggests that all information in a volume of space can be encoded on its boundary. This might mean that what we perceive as motion through three-dimensional space is actually information flow on a two-dimensional surface. If true, faster-than-light travel might be impossible not because of energy requirements, but because it would violate information theoretic limits, more fundamental than space-time itself. The engineering challenges of maintaining human life during interstellar travel reveal stark differences between our two technologies. At near light speed, a journey to Alpha Centauri might take only months from the crew's perspective, but they'd need systems that can function reliably for decades of Earth time without resupply or external maintenance. Every component would need unprecedented redundancy and self-repair capabilities. With warp drive, the challenge shifts to maintaining life support within a bubble of warped space-time where normal physics at the boundary might create lethal conditions. Recent breakthroughs in closed-loop life support systems on the International Space Station provide sobering context. Even with regular resupply from Earth, the ISS achieves only about 93% water recycling efficiency. For interstellar travel at any speed, we'd need nearly perfect recycling of air, water, and nutrients. The difference between 99% and 99.9% efficiency could mean life or death over interstellar distances. The discovery of Tabby's star, KIC 8462852, and its unusual dimming pattern sparked speculation about alien megastructures, but also highlighted how advanced civilizations might harness energy for interstellar travel. Even if the dimming is natural, it reminds us that any civilization achieving routine interstellar travel would need energy collection on stellar scales. Dyson spheres or similar constructs might be prerequisites for either sustained near-light speed travel or warp drive technology. Let's examine what computer simulations tell us about the feasibility of each approach. Molecular dynamics simulations of materials at relativistic speeds show that even diamond would erode quickly when impacting interstellar hydrogen at 90% of light speed. Each hydrogen atom would hit with the energy of a cosmic ray, gradually destroying any material shield. For warp drives, simulations of the Alcubierre metric show that quantum fluctuations at the bubble boundary would likely destroy the field configuration in nanoseconds without some unknown stabilizing mechanism. The possibility of using black holes for interstellar travel presents intriguing options for both approaches. The gravitational slingshot around a black hole could accelerate spacecraft to extreme velocities, potentially reaching speeds where time dilation becomes significant. Some proposals even suggest using rotating black holes, Kerr black holes, to create closed, time-like curves, though this ventures into highly speculative territory. For warp drives, the extreme space-time curvature near black holes might provide insights into space-time manipulation. Recent observations of neutron star mergers by LIGO and Virgo have confirmed that gravitational waves travel at exactly light speed, not faster or slower. This measurement, precise to within 1 part in a quadrillion, reinforces that the cosmic speed limit applies to space-time itself. If gravity respects this limit, it suggests that any manipulation of space-time for propulsion must also respect it, casting doubt on faster-than-light warp drives. The concept of vacuum engineering represents a frontier where both technologies might find breakthroughs. By manipulating quantum vacuum fluctuations, we might reduce inertia, making acceleration to near light speed easier, or create negative energy densities, potentially enabling warp drives. Recent experiments with metamaterials have shown we can alter vacuum properties locally, though extending this to spacecraft propulsion remains highly speculative. Consider the economic implications of successful development of either technology. Near light speed travel would create a society of time-separated civilizations, where trade involves decade- or century-long round trips. Economic models would need to account for relativistic time dilation in ways never before considered. Warp drive would enable real-time interstellar economy, but might concentrate power in the hands of those controlling the technology, given its presumably enormous cost and complexity. The frame-dragging effect, confirmed by NASA's Gravity Probe B, shows that rotating masses drag space-time around them. This effect, while tiny for Earth, becomes significant near rotating black holes. Some warp drive proposals incorporate rotation to reduce energy requirements, using frame dragging to help create the necessary space-time distortion. Understanding natural frame dragging helps us evaluate whether artificial space-time manipulation is achievable. Recent studies of quark-gluon plasma, created in heavy ion collisions at the relativistic Heavy Ion Collider, RHIC, reveal matter behavior at temperatures exceeding 4 trillion degrees Celsius. This state of matter existed microseconds after the Big Bang and might exist in the extreme conditions of relativistic spacecraft shields or warp bubble boundaries. Understanding matter under such extreme conditions is crucial for both technologies. The discovery of Planet 9's potential existence through its gravitational effects on trans-Neptunian objects demonstrates how we can infer the presence of massive objects through their space-time distortions. Similarly, we might detect advanced civilizations using warp drives through their gravitational signatures long before we develop the technology ourselves. The absence of such signatures in our observations provides empirical constraints on how common faster-than-light travel might be. Plasma wake-field acceleration, achieving acceleration gradients thousands of times stronger than conventional accelerators, offers insights into pushing particles to extreme speeds. While designed for particle physics, these techniques might scale to spacecraft propulsion. The AWAKE experiment at CERN has demonstrated acceleration of electrons to giga-electron volts over just meters, showing that extreme acceleration is possible with the right approach. The relationship between information theory and space-time suggests fundamental limits to both technologies. The The Bekenstein bound limits the information content of any region of space. The Margolis-Levitin theorem sets a maximum rate of information processing based on energy. These limits might constrain how fast any spacecraft can process navigation data or make decisions, potentially setting practical speed limits below the theoretical maximum. The astrobiology implications of each technology profoundly affect how we might discover and interact with alien life. At near light speed, any biosignatures we detect before departure would be decades or centuries old upon arrival. Life that appeared thriving through our telescopes might be extinct when we arrive. Conversely, sterile worlds might have developed life during our journey. With warp drive, we could respond to biosignature discoveries in real time, potentially arriving. While detected, life is still present. But the energy release from dropping out of warp might sterilize any life we came to study. Recent advancements in quantum computing have implications for both technologies. Quantum computers could solve the complex field equations required for warp bubble stability in real time, potentially finding configurations that classical computers could never discover. For near-light speed travel, quantum computers might enable navigation through the severely blue-shifted and aberrated star field that relativistic travelers would experience. IBM's recent achievement of quantum supremacy with their 433-qubit Osprey processor represents early steps towards such capabilities. The discovery of organic molecules in interstellar space has revealed that the building blocks of life are widespread throughout the galaxy. At near-light speed, spacecraft would plow through clouds of these molecules, potentially collecting samples from thousands of light-years of space. This natural mass spectrometry could provide unprecedented surveys of galactic chemistry. With warp drive, you'd bypass this material entirely, missing opportunities for scientific discovery during transit. Let's examine what the silence of the cosmos might be telling us. The Fermi paradox becomes even more puzzling if faster-than-light travel is possible. With warp drive, a civilization could colonize the entire galaxy in thousands rather than millions of years. The fact that we see no evidence of galaxy-spanning civilizations might suggest that faster-than-light travel is fundamentally impossible, or that civilizations choosing to develop it face some unknown catastrophic filter. The role of metamaterials in achieving these technologies deserves special attention. Metamaterials with negative refractive indices can make light appear to travel backward, though information still propagates at or below light speed. More exotic metamaterials might manipulate gravitational fields similarly to how current ones manipulate electromagnetic fields. Research at institutions like Duke University and Imperial College London is pushing the boundaries of what metamaterials can achieve. Recent observations of white dwarf stars have provided natural experiments in extreme gravity and density. Some white dwarfs spin at rates approaching their breakup velocity, creating relativistic effects we can observe from Earth. The white dwarf SDSS J221141 821133328.3 completes a rotation every 70 seconds, approaching the theoretical limit. These natural laboratories help us understand matter behavior under conditions relevant to both relativistic travel and space-time manipulation. The concept of induced hibernation or suspended animation changes the calculus for near-light speed travel. If humans could be placed in reversible stasis, the subjective experience of time dilation becomes less relevant. Recent breakthroughs in understanding how some animals survive freezing or extreme metabolic reduction might lead to human applications. This biological approach might make near-light speed travel more practical than pursuing faster-than-light physics. Consider the warfare implications of each technology. Near-light speed kinetic weapons would be virtually unstoppable, with even small objects carrying civilization-ending energy. A 1 kilogram mass at 90% light speed carries kinetic energy equivalent to 43 megatons of TNT. With warp drive, the ability to appear anywhere instantly would make defense impossible. The existence of either technology would fundamentally destabilize any multipolar interstellar civilization. The discovery of axions, if confirmed, could revolutionize both approaches. These hypothetical particles, possibly constituting dark matter, interact extremely weakly with ordinary matter but might be manipulated to create exotic field configurations. Some proposals suggest axion fields could reduce inertia or create negative energy densities. The ADMX experiment at the University of Washington and similar searches worldwide are hunting for these elusive particles. Recent studies of cosmic voids, regions with far fewer galaxies than average, have revealed that space itself can have radically different properties depending on matter density. In voids, dark energy dominates more completely, causing faster expansion. Understanding how spacetime behaves in these empty regions might provide insights into creating artificial bubbles of altered spacetime, whether for protection during near-light speed travel or for warp drive implementation. The phenomenon of pair production from vacuum fluctuations observed in ultra-intense laser fields demonstrates that empty space can be converted into matter and energy. The extreme light infrastructure being built in Europe will push these experiments further, potentially revealing new ways to manipulate the quantum vacuum. While far from practical propulsion applications, these experiments probe the foundations of spacetime in ways relevant to both technologies. Machine learning algorithms are increasingly important in solving the complex optimization problems both technologies present. Google's DeepMind and similar AI systems could potentially discover warp field configurations that human physicists would never conceive. For near light speed travel, AI could optimize trajectory planning through the complex gravitational landscape of the galaxy, finding paths that maximize time dilation benefits while minimizing radiation exposure. The discovery of ultra-diffuse galaxies has shown that large-scale structures can exist with far less matter than previously thought possible. These galaxies, as large as the Milky Way but with only 1% of its stars, demonstrate that spacetime can maintain structure with minimal mass energy. This might suggest that the energy requirements for spacetime manipulation could be lower than current estimates suggest, though still enormous by human standards. If you made this far, please make sure to subscribe and give a thumbs up. Your support means a lot to me, and if you like this video, you will love this other one at the left side of the screen. If nothing exists outside the universe, what is it expanding into? If you're fascinated by space, time, quantum physics, and the biggest questions in science, don't miss this deep dive into the expanding universe. See you there.